Now we are
like a live thing.
Now we are live on YouTube. All right, so today is my great pleasure to introduce our guest lecturer, Dr. Liz Munch, and she is currently a faculty from Michigan State University. So Dr. Elizabeth Munch is assistant professor at Michigan State with a primary appointment in the Department of Computational Mathematics, Science, and Engineering, and a secondary appointment in the Department of Mathematics. Her research specializes in applied topology and topological data analysis. She received her PhD from Department of Math at Duke University in May 2013. And prior to joining the faculty of Michigan State, she was assistant professor in the Department of Mathematics and Statistics at University of Albany and SUNY. And she was a postdoc fellow at the Institute of Mathematics and its Applications at the University of Minnesota from the 2013-2014 thematic year on application of topology. She also has a Master of Arts in Mathematics from Duke, a Bachelor of Science in Mathematics from University of Rochester, and a Bachelor of Music in Harp Performance from Eastern School of Music. So today she's going to talk about application of TDA for time series analysis, and I was secretly hoping she will also talk a bit over plant morphology as well as hurricane. So those are my special requests. Hopefully she can talk about a bit towards the end of her talk. Yeah. All right, Liz, go ahead.
Hey, thanks, Faye. Yeah, I did at least throw some pictures in at the end so we can kind of chat about some of the other stuff. Because yeah, I do a lot of things, and I had clearly a very strange path to get to my current job, which I kind of love. It's just been interesting. So right, so my PhD's in math. My primary appointment now is in not a math department. So CMSE is a sort of newer department. It's only about 5 years old at Michigan State. And we do sort of the intersection of applications and computation and data science and high performance computing and all sorts of other fun stuff. And it's very interdisciplinary and it's a lot of fun. Yeah, so let's see. So what I'm gonna talk about, for at least to start, is mostly my work on time series analysis. And so the idea being that you can take, and I'm going to assume that you all have been talking about a lot of this stuff, but I'm going to give you some background anyway, just in case, but how you can take the tools from TDA and use them for time series analysis applications. So the general game, right? So again, this is preaching to the choir, but the whole game with TDA is trying to find ways to quantify shape in data. And so my research spans the gamut from, so we've got some applications in hurricane analysis. So this was work with my graduate student, Sarah Tomachko. We've done a bunch of work on analyzing plant morphology kinds of things. So this tends to be closer to like the image processing realm. So for instance, you can see here, let's find out if this guy works. You can see, so these guys right here, these are X-ray CT scans of walnuts. So we have this lovely data set where we put all these walnuts into a giant X-ray CT scanner, and we're trying to figure out how we can use TDA kinds of things to analyze how easy it is to crack a walnut, which is, I find, hilarious. But then there's also all sorts of other things where you might be looking for like shape in data. So a lot of the other things that I do are related to things like Reeb graphs, which are over here. And so the idea is like, can you skeletonize your data in a way that's useful? And can you compare it to other things? This is actually a bunch of the work that I've done with Bay, the fabulous and wonderful Bay, who's over here. So we were doing a lot of things related to like convergence of mapper graphs and things like that, which I'm not really going to talk about today either, but I think it's cool. So right, so whenever I'm starting a new TDA kind of project, this is sort of the overall pipeline that we're trying to figure out how to put all the pieces together. So I've got some sort of input data, which depending on the application is all sorts of different things. It could be X-ray CT scans, images, point clouds, networks, lots of different sort of starting input things. But the idea is always to try to get that thing into some sort of topological signature I can use to represent what's going on with the underlying shape and structure, right? So, and I'm sure you guys have all talked about these things, but things like persistence diagrams, Euler characteristic curves, mapper graphs, Reeb graphs, merge trees, contour trees, I'm missing something, right? But the idea is to take your input data and represent something about the underlying shape and structure. And then once you get there, right, if you're doing things on actual data sets, then you want to be able to do some sort of analysis to understand what happens. And so this shows up in a lot of trying to figure out how to take your topological signatures and turn them into some sort of statistical analysis or machine learning framework or some way of actually interfacing with the existing things, right? So if I have 300 walnuts and then I want to compute Euler characteristic curves for those, and then I want to do statistics on those to try to understand something about my original walnuts. And so a lot of what this is trying to get back to the domain scientists to try to, communicate to them what these TDA representations mean, which is already difficult in its own right, because, algebraic topology is not your standard biologist's background. But then also to use it to try to actually answer their questions. So then a lot of what we're doing is trying to figure out how to make that middle step, the topological summaries that you're working with, really nice in any sort of theoretical framework you might want. So quantifiable really just means that I can actually compute these things in any sort of reasonable amount of time. Comparable means we spend a lot of time trying to understand metrics. Robust in the sense that according to those metrics, you should be relatively resilient in the face of noise, and concise in the sense of you've got a sort of simplified representation of your shape and structure, right? So rather than having to have the entire X-ray CT scan of my plant over here, I can hand you a persistence diagram, and hopefully that is, a decent representation of what you're doing. Right, okay, so if we're going to do time series analysis types of things, the trick is then to take some sort of input time series and turn it into something that you can analyze the shape and structure of, again, with the viewpoint towards, can I understand my starting dynamical system that I got my time series from via my representation of shape and structure. And so in this case, so I've got a sort of noisy sine curve on the left, but I've got this, example input time series. And so what I can do is use this trick called Tokens embedding, which basically embeds my time series as a point cloud in Rn space or wherever you want to live. And in particular, this has nice properties in terms of trying to reconstruct your original attractor. So in the case of this guy, right, so I've got a periodic time series input, right? So I've got something that's basically just this wiggly sine curve. And so what ends up happening is if you go around in circles, periodic behavior this way, once I do this Tokens embedding behavior turns into periodic behavior this way. And as we all know, persistence is particularly good at finding circles. And so we can measure something about the structure of your original time series based on something about the structure of your point cloud that you've constructed. Right, so the game for a lot of this stuff is trying to distinguish behavior based on your persistence diagrams or whatever other representation you're doing. Right, so if in this sort of case, so if you end up starting with time series and you get this point cloud, so the most standard way to get to persistence from a point cloud is to use check complexes or RIPS filtrations or some variant of that, right? So the idea being that if I do something like the union of disks around a bunch of these points, right? I can look for when the circular structure appears and then gets filled in, and that gets represented as a persistence diagram, right? So I'm going to, I'm kind of assuming you all know this already, but just for completeness, right? So I have overarching circular structure in my example point cloud here, represented by this point in the persistence diagram. And so the green line passes it right about the time the overarching circular structure starts, so right around there-ish, and then fills in by the time you get the red line past it. And so the other thing that's going on in here is if you've got points that are close to the diagonal, points that's close to the diagonal, at least in this context, tend to mean noise. And so for instance, if you look for this point right here in my persistence diagram, that's being computed because I've got some circular structure that shows up right around here that appears and fills in really fast. And so I end up having a bunch of points near the diagonal. The perk of this whole construction, though, is that I can sort of differentiate what I mean by signal versus noise in terms of the overarching structure. All right, so here's kind of the pipeline that I'm going to talk about various bits of today and sort of how we've been messing around with these ideas. So the standard, for whatever definition of standard, pipeline for doing all of this that I was sort of just talking about is to take your time series, turn them into your embeddings. So this is, I don't remember if I said this before, but this is sometimes called Tokens embedding or delay embedding. Usually what we do is then construct a RIPS filtration, which essentially takes that point cloud and looks at a pairwise distance matrix. So you can look at the distance between any pair of points. And you can construct a simplicial complex by something to do with a proximity parameter. Once I have some sort of distance matrix, I can always construct a persistence diagram using essentially click complexes or the like. And then once I get there, because I want to do analysis, I got to find a way to get some vector representation of my persistence diagram to actually do statistics and machine learning and things like that. For the purposes of today's talk, this is going to be the relatively simple examples, and we're going to kind of talk about how to mess around with this sort of starting path in this diagram, but replacing some of these options with other ways of getting into representations of time series that we can use and combine with persistence diagrams. Okay, so it's very possible you guys have seen a lot of this stuff, so my apologies in advance. And also, please feel free to stop me and ask questions. I'm happy to explain myself more, since I don't know if I'm going too fast on any of these chunks. All right. So the first bit I'm going to talk about is essentially the last portion, which again, I think you guys have, where'd my pen go? This last portion that I think you guys have probably seen at this point, right? But if I have pairwise distance information, I can get a persistence diagram out. So clear. Here we go. All right. Behave. There we go. Okay. All right. So here's one way of thinking about getting to persistence diagrams from some sort of filtered topological space, right? So you have some sort of topological space, you have a filtration, right? So usually I'm going to think about these as being nicely behaved simplicial complexes. Magic of functors and category theory mean that I can turn all of these inclusions into a bunch of maps on homology, right? And so I can immediately replace this filtered simplicial complex with this sequence of maps on homology. And in my world, everything is over probably Z2 coefficients. These are all vector spaces. My life is very nice. But the whole perk here is that I can take this persistence module, this sequence of vector spaces, and break it up into these interval modules. So interval modules are essentially a sequence of vector spaces that have zeros for a while. So this is supposed to be my vector space is defined over the field K. I've got my vector space K for a while, and then it goes back to being zeros. And my maps here are identities when they can be and zero otherwise. And what I can do is I can break this thing up into all these pieces. I can look at sort of where this interval chunk happened and keep track of that information. And then from there, if I know that I've got this collection of interval modules that start at A and end at B, I draw a point at A comma B for that particular interval module. And because of nice theorems, you always get the same decomposition up to isomorphism. And so persistence diagrams are well defined.
So I'm going to insert a little bit, because actually in this class, I intentionally avoided all the algebraic treatment of persistence modules.
But it's so pretty.
What's that?
It's so pretty.
I know you appreciate the mathematical beauty, but to connect to what folks has learned so far, what she has there from K, arrow, to K, that you can interpret basically as the first K is where you see the burst time, the last K is where you see the death time. So essentially those kind of consecutive vector spaces in the persistent module basically correspond to the burst time and death time, which is basically the barcode. Right. So this is more of an algebraic treatment of this, but the end result is that, in the middle, there's, this whole interval decomposition is just to say, if you give me the sequence of homology connected, you can basically go through the computation. In this particular case, it's called decomposition, but it's in practice, it is the algorithm we have went through, which is how do we compute persistent homology. It will give you the points in the persistent diagram. Equivalently, it will give you the interval as your barcode, in the bar in the barcode. So this just went a bit into the algebraic treatment of it.
Yep.
Okay, go ahead.
It's
Sorry,
all
Liz.
the same. Nope, it's all good. This is what I need, because I haven't been in your class all week. Well, I got to teach this class in the fall, so I need to figure out what I'm doing. We'll talk later. Right. Okay. So once you get to the input filtration output persistence part, then the game is that you can come up with a filtration on a simplicial complex automatically given any sort of distance function. All right, so what do I mean by that? So I have a set of some finite collection of objects, which I'm going to call vertices. And I have some definition of a distance. So any notion of taking two vertices and telling you how far apart they are. What I can do is I can build a complete simplicial complex with vertices V. So if in this case, if I had 4 vertices, I'd have a complete simplicial complex with everybody involved in the middle. And I can stick a weight on each of the edges based on the distance between U and V, right? So the nice trick here is that you can extend this up to the, so I guess I drew you a complete graph. I want to get a complete simplicial complex. And so I can give a weight to every simplex in my simplicial complex by looking at the maximum value of all of the pairwise distances. So for instance, if I'm interested in this particular triangle, the weight I'm going to give to that particular triangle is going to be given by the maximum of all of the edges involved in my triangle. So the maximum of that distance, and that distance. And so that gives me a sort of a function, a simplicial function on my complete simplicial complex. And so then what I can do is I can build a filter based on that, right? So now what I'm going to do is make K sub A be the portion of the simplicial complex where simplices have function value less than or equal to A. And because of the way that I've rigged this whole thing, I get a well-defined simplicial complex at every step, right? And I can sort of build it up accordingly, right? If you were to do this with starting with point cloud in Euclidean space, right? Everything I just told you would be the Rips complex. So this is sort of the generalization of the sort of point cloud version you probably have seen before this. So in the point cloud version, so this is the Rips complex, right? Where you basically take the subset of your initial point cloud for which the pairwise distances are all less than or equal to epsilon, and you end up with the same thing I just said, right? And so we can get a filter on these things by just expanding the distances I'm looking at, filling in all the simplices accordingly, and then I have a loop that fills in and takes a while, and then it fills in. Okay, so what I want to do is I want to swap out that distance definition for something else. So let's say my input data is a graph now instead of a point cloud. So what I can do is I can start with my graph on the left. There are labels on the vertices that have nothing to do with anything, so just ignore those. That was from, I don't remember why we had the labels on the vertices. But I can define a distance between any two vertices in my initial graph by looking for the shortest path distance. So in this case, my shortest path probably goes that way. So my distance between vertex 6 and vertex 18 is 1, 2, 3, 4, right? And so I can keep track of all of that information, right? So pairwise distance between any two adjacent vertices is 1. And if you go further around, you can get larger values. So what we can do with that is then construct basically this Rips complex filtration based on this distance that I've defined. All right, so what ends up happening? I really need to label this picture. Keep saying I'm going to do that. All right, so if I take all of the points that are within distance 0 of each other, I get just the vertices themselves. If I take all of the points that are within distance 1 of each other, that gets you back your original graph because every vertex is 1 away from all of its adjacent vertices. And then as I go higher, K4, K5, we end up seeing more and more of this simplicial complex. Right? Despite the geometric-y embedding thing that I'm drawing here, remember these are abstract simplicial complexes, but at least in this lovely way that I've drawn it, you can kind of see where the loops are. So the loops that are going on in here, right? I've got 2 circular structures that are showing up, one and the other, right? And so this first guy, if I follow it along, ends up getting filled in somewhere in here. And the second one, what else is going to show up? Green? The second one, right? I've got a second loop structure that shows up here and ends up getting filled in at K4. So what happens here is that I've got this persistence diagram. Sorry, I have my labels in the way of my picture. I've got this persistence diagram where I have 2 points in my persistence diagram. Each of them are born at time 1 because that's when they first appear, and 1 dies entering 4, so I get a point at 1, 4 for this guy, and for the other loop I have my point at 1, 5 because it dies entering 5. So I can get these persistence diagrams, and in the case of graphs and the way I've rigged this up, they are relatively simplistic, right? Because I've basically rigged this thing so that everything is born at time 1, and then you're sort of mostly just interested in death times for these. Okay, so where are we? So far I've got a way of getting from distance matrices to persistence diagrams. I also have a way of getting from a network to a distance matrix. And so what I'm going to show you next is essentially ways of getting from time series into point clouds and permutation sequences, all sorts of different ways of messing around with representing your time series. All right, so tokens embedding, right? So, okay, we showed this already, but here's for completeness. Oh, come on, behave. There we go. All right, so tokens embedding. So the whole idea behind tokens embedding is that you can take your input time series. I have to make 2 decisions in advance. I'm going to decide what dimension I'm going to embed my time series in, and I need to decide on a delay parameter. So dimension is going to be, I believe, d in my notation down here, and delay is going to be tau. And so what I'm going to do is I'm going to take a comb, at least that's the way I think about it, with d teeth, right? So in this case, d is 3. So I take my comb with 3 teeth, I evenly space them, and I look at the function values at those 3 locations. So for this guy, maybe I can stop this for a sec. Yeah. So this guy, right? So if I've got time, where's my pen? Where is that color? There we go. So this would be t plus tau, t plus 2 tau, right? Sorry, my writing's getting bad. Right, so I've got my 3 teeth in my comb, and I can look at the points that are at the function values at those 3 times, right? So what I can do is I can forget the fact that I got these from a time series and just treat these as a vector in R3 in my example, all right? And so what ends up happening is for each location I put this comb, essentially I can just kind of slide it along, each of those locations ends up drawing a point in my point cloud, which should be the red triangle that you can see on the right. Right. And so the magic secret sauce of this whole party is that you got to go figure out good choices of dimension and delay, because if you don't do that, you end up with these kind of garbage representations. This is a long and very deep field that has a whole lot of methods for doing this. There's sort of tricks based on information theory to try to figure out what tau you want to pick. There are tricks based on essentially false nearest neighbors is a way of coming up with the dimension, where you essentially look at embedding this thing in higher and higher dimensions and finding out when you stop sort of gaining abilities based on going to a higher dimension. Right. But this is basically done in advance for us. So I'm going to assume for the moment that this has all been taken care of and we have everybody embedded in a nice location to start doing the rest of this. Okay, so here's our first way of getting through this pipeline. How do I get from time series to persistence diagram to vector representation? All right, so I've got my parameters d and tau. I can construct my point cloud, and then I can compute my distance matrix and just compute the persistence diagram. So this is basically well studied at this point, right? So I can do the sort of standard RIPS complex point cloud version of all of everything I want to do. So here's an example of doing that. So this is time series generated from the Rossler system with 2 different parameters. I believe the one on top is parameters chosen to be periodic, and the second one to be chaotic. And so the idea here is that if you follow through this pipeline, you get this persistence diagram out. And in this case, I have sort of an overarching structure that's, relatively nice and circular. And I can kind of stare at this and convince myself that maybe like this is, my major representation for this point cloud. And hey, I don't really have any interesting points in my persistence diagram down here. And isn't that lovely? So they are very different. And so I can differentiate my original time series based on my persistence diagram. So that is nice, but let's mess around with some other versions of this. So here's the what I can do if I instead want to come up with a K-nearest neighbor graph based on the same information. All right, so what's a K-nearest neighbor graph? So if you give me a point cloud embedded in whatever land you want it to be in, I'm going to work with an undirected, unweighted version of my K-nearest neighbor graph. And what I'm going to do is I'm going to add an edge between U and V if V is one of the K closest neighbors to U, right? So you look at all the neighbors of, make sure I get this right, all the neighbors of U, you look at its K closest neighbors and you add an edge to all of those. All right. Right, so this involves picking a K in advance. But what we can do is that once we've built this K-nearest neighbor graph, now what I can do is I can do everything I said before about distances and come up with pairwise distances, which I can do to build persistence diagrams and then go from there. All right, so here's what happens when you do that with the same time series. So I've taken all my data. I'm doing. Yeah, sorry.
So when you do the K-nearest neighbors and say you get disconnected components at the end, what do you put in the distance matrix? Is it infinity?
Multiple connected components? Yeah. So everything I'm doing ends up with just single connected components. That's a very good question, but yeah. Let's see, where were we? Sorry, did that answer your question? Is that good?
So what would you do if there were multiple components? Can you just put infinity in the distance matrix and let whatever happens happens?
Yep. Yeah.
Okay.
So when you start doing these computations, right, a lot of the standard tools are you'll end up with a zero-dimensional class that lives forever.
Can you say it one more time? I think we lost you for like 5 seconds. So maybe
sorry, my internet's terrible. Yeah. Okay. So yeah, what I would do in that case would be to have, if you've got two connected components, the distance between U and V, if they're in different components, would end up being infinity or whatever, in practice, whatever large number you want to decide is infinity, right? And so then what's going to happen in your persistence diagrams is my zero-dimensional diagrams will have a point in my persistence diagram that's at 0, until forever. Right. So at the end of the day, I don't think it's going to affect too much. I'm more interested in sort of the underlying structure of the main connected component. So that's a very good question. Cool. Any other questions while I'm? All right. And like I said, please feel free to stop me. I'm happy to take questions. So I picked a K. I don't remember what K was when we computed this. I want to say either 2 or 3. But I can do the same, like compute my distance matrix and compute my persistence diagram. And what's very nice about this is that I sort of have a very cleaned up representation as opposed to the RIPS complex version. So the first thing I'll point out to you is the fact that my axes are different. So this has, maximum 9, which actually stops. For my little hairball experiment down here is actually living all the way down here and is essentially noise compared to this prominent point that I can see further away. All right. So let me just mention something else about my drawings, in particular, because we're doing a lot of things with integer valued lengths and distances. It's very possible that you can have more than one persistence diagram, more than one point in your persistence diagram drawn on top of itself. So in my pictures, I've also got a histogram drawn on the right where I'm telling you how many points there are at that particular lifetime. So in this case, I have one point that's right here. In the example down here, my point at 1, 2 is actually, what's that, 7 or 8 points, right? And so I sort of have just things drawn on top of themselves. Okay, so, all right. So let me show you another way of getting from time series into networks. So there's this lovely construction from the last few years done by Small et al., where they were interested in essentially representing something about your embedded space in a network. All right, so here's how we get there, and then I'll show you a picture that I think will make more sense than the actual definition. So again, fixed parameters d and tau in advance. I can construct my point cloud embedding, but what I can do is I can construct what's called the ordinal partition network. That's the only thing that's switched in here. Everything else is the same. So what's the ordinal partition network? So if you give me a vector, so a point in Rn, I can look at the permutation, which is the essentially ordering of the points so that they're sorted, right? So what permutation of the indices do I need to get them into sorted order? So once I do that, what I can do is I can take every point in my point cloud representation and associate it to a vertex, which has to do with its permutation. And then I can add an edge between two of these permutation vertices anytime I pass from one of those representations to the other, right? Okay, so let's take a look at that because I don't think this is helpful for things. I think I need examples. All right, so on the top left over here, so this guy is my input time series. And so these 3 points are still that sort of same trick where I'm looking at sort of evenly spaced points. And what I'm interested in is essentially the shape of the red line. So this red portion that goes up and then down in the middle. And so there's 6 possible options for this choice of parameters. So I've got 6 different places you could end up, right? And so if I were to stop at, let's stop so I can actually look at something. Oh, I stopped at a bad location. How about there, right? So this particular choice of point in my tokens embedding, what I have is I have middle, lowest, highest. So middle, where is it? Middle, lowest, highest is pi3, just under whatever this ordering is. And so this particular point gets associated to this particular node, which is pi3. And then if I pass a little bit further along, right, this thing is going to go from pi3 probably to pi1. And we're going to end up moving from one of these vertices to the next. So what's nice, again, if you notice, we're still doing things with periodic looking signals. And so this ordinal partition network ends up giving me very nice sort of circular structure. So again, this is a combinatorial graph. So if you unfold that thing, it is actually a cycle graph. There's some information in here that we are not necessarily using for this particular project, but is our sort of next step, which is we do have directed information, and we have sort of information in terms of how frequently you move from one point to the next. In this case, you only have one place to go. But there's some weighted and directionality information that I'm going to drop for the purposes of this talk, but we're working on that at the moment. Okay, so here's what ends up happening in this case. So here's my quasi-periodic, periodic input time series. When I do this ordinal partition network, what ends up popping out of this is this sort of nice overarching loop structure. And so again, you can see that I've got sort of, in this case, it ends up sort of showing me 2 prominent loop structures. But in any case, I'm very different from my noisy representation down here because again, my x-axis, my 6 is somewhere up here. So all of this diagram is kind of contained down in noise land in the bottom. Okay. Yeah, there's parameters. We spend a lot of time trying to figure out the parameters. There are ways of basically coming up with D and tau specific to this construction. I'm not going to worry about it for the moment. It's basically based in information theory. We have to spend a while trying to figure out D and tau. This is what I think is cool. So what's going on in here is these permutations. What you're actually doing is you're essentially breaking up state space into regions based on hyperplanes that are of the form xi less than or equal to xj, right? So you take all of these hyperplanes and you stick them in space. And what you're actually doing here is any of your representations have to do with which portion of state space you're actually sitting in, right? So if I'm in the pi1 was, I don't remember if that was x1 less than or equal to x2, x less than or equal to x3, I'm somewhere in this giant wedge of the space. And so whenever my point lands in there somewhere, that's actually the permutation representation that I'm working with. So what's nice about this whole thing is that there's some very nice connections to geometry and in terms of what's going on. But this is also why, for instance, in this case, because of our choices of parameters, I ended up with 2 loops in that other graph structure, right? Because being in this part of the wedge versus being in this part of the wedge are basically seen as equivalent. Okay, so let me show you what we've done with this. So let's see. So in the first version of the pipeline, right? So I haven't really talked much about how you get from persistence diagrams into vectors, but this is sort of one of the first examples of these things that we did, which was we could take, all right, so you have time series that are generated in this case from the, this is Rossler system again. And I can vary a parameter in that system and get a whole bunch of time series. So every choice of alpha, so in here, every choice of alpha down here gets me a different time series. So every time series gets me a persistence diagram representation. And so what we ended up doing was trying to classify the time series of whether they were periodic or chaotic based on whether or not they were so based on having some ground truth of that labeling. So we used what's called the Lyapunov exponent to decide on the ground truths. This is something that is sort of a standard tool from time series analysis, but has its own error issues, also computation time. So what we did was we used that as our ground truth. And we built a supervised learning model where essentially we took our persistence diagrams, turned them into some sort of vector representation. Again, I'm not going to go into that in this talk, but so we used template functions, which was a system we were building and trying to test in terms of how to represent persistence diagrams, and then labeled our misclassified things, right? So in this case, we stuck a misclassification label at the entire portion of this bifurcation diagram. And so what had happened, which makes me feel good about how we're doing this, is that essentially the places that we were having issues with misclassification show up right on boundary, right? So in this case, the pink regions are the chunks that are periodic, right? And the white regions are the chunks that are chaotic parameter values of alpha. And so we ended up having, relatively decent, I consider this a good job. I forget what we had in terms of percentages, but the errors we're having are on the boundaries, where I'm not always convinced that Lyapunov is doing a great job anyway. And so we're sort of doing a decent job based on our input data.
So Liz, I have a quick question. I'm trying to understand this plot. So is a circle means classified well, and then the pink diamond means they're not classified well?
No, those are misclassified. Yeah, sorry. So we did an 80-20-ish split, 70-30, something like that. And so we trained on a bunch of our data and then tried to figure out which values of, I probably should redraw this picture to be more accurate, but try to figure out which values of alpha got misclassified, right? And so something in here got misclassified as periodic when it's not, something in here got misclassified as chaotic when it's not, etc.
But I only see one color for each of those things, which means they all seems to be well classified. Like which dot is an example that is misclassified?
Yeah, so all of the dots, sorry. So yeah, so the sort of better way of drawing this picture would probably be more like, so here's my values of alpha, right? And so each of those dots ended up getting redrawn at every location of the bifurcation diagram. So this is actually like one misclassification that happened at 0.38-ish, if that makes sense.
Oh, so all those are misclassified classes.
Yeah, and there's there's multiple dots representing one misclassification. So yeah, that's a good point. This is probably not the most intuitive way of drawing this.
Okay, I
basically
might come back
the way
to
that
it
I would
later.
interpret this is like misclassifications happened at these alpha values approximately, right?
Oh, and then the rest where there's like this blue, that means they are not misclassified.
Yeah, exactly. So this stuff is all, nothing was misclassified for any of these alpha values, nothing for these alpha values. And then errors happen sort of on boundaries. Good question. Any other questions while I'm here? Okay. All right. So let's mess around with some of our other network representations. So for the other network representations, we use some much simpler versions of how to represent our persistence diagrams as vectors, partially because we've got very simple input diagrams to begin with. Remember, once we do networks, all of my diagrams have one-dimensional classes at 1, 0, or whatever it is. Born at time 1, die at something, right? And so that's sort of our interesting bit. So the first version of this that we used to represent our persistence diagrams was persistent entropy. So this is a definition that came from about 2015. And so this is essentially coming from information theory and trying to like represent your persistence diagram structure via information theory. So what's going on in here is I have some like total lifetime, which is my, okay, so pers of x1, x2, that's supposed to be lifetime of any point in my persistence diagram. Total lifetime is the script L. So you take all of your lifetimes and sum them up. And we end up with this log computation up here. For what we were doing that wasn't working particularly well, we ended up working with this normalized version instead. So anytime you see this E prime of D, this was our normalized persistent entropy computation that we were using as representative. Another thing that we did to try to represent the structure was to come up with this periodicity score. So what we did was we were essentially trying to compare how far off our resulting persistence diagram was from being a cycle graph. So in this setup, right, so I have essentially so you can ask the question, what would my birth and death time be of the single point in the persistence diagram if I just gave you a cycle graph? And so in this case, you can sit there and compute floors and ceiling functions. But if you give me a cycle graph of length n and you compute its persistence diagram, you end up with a point at 1 comma the floor of n over 3 based on sort of where things match up. And so our lifetime ends up just being this, ceiling of n over 3 minus 1. And so we rigged up this score in such a way to be sort of a measure of how far off you are from being a cycle graph, right? So the maximum persistence of the graph of the diagram you actually saw divided by what it would have been if it was just a cycle graph, and 1 minus to make this go in the direction I wanted to. What is it? So if it is a cycle graph, it should be 0. Is that right? Because the max pers would be equal to ln, yeah. And if it's the further it is, the further away from 0 it gets. I call this one the other one because we've got a lot of pictures with it. I'm not sure I like it because I don't have a lot of theoretical justification for it, but here we are. So what I can do is I can start with a diagram that has D off diagonal points and compute this M score, which is the number of off diagonal points divided by the number of your original vertices. So it's sort of related to the reciprocal of the number of nodes per one-dimensional class on average, but it's a little bit fuzzy. I'm not sure I like any sort of theoretical justification. In any case, I've got it on a bunch of pictures, so I want to make sure it's in here. Okay, so what do we got? So here's what happens if I try to sort of score my periodicity from my time series based on these different outputs. So this is the case where we did the k-nearest neighbor graph. And so the green regions now are the portions of the parameter space that are periodic, and the white ones are chaotic, I believe. And so what we were doing was essentially comparing my k-nearest neighbor measurements that we were getting. So these middle ones are via the persistence diagram computations, and comparing them to what happens sort of the sort of standard models. So people have been using these already, but they were using sort of standard graph theory representations, right? So in this case, they were computing things like the mean out degree of the vertices in the network, the variance of the out degree, et cetera. Whoops, nope, go back. That one. All right. And so we sort of came to the conclusion that our persistence-based representations are differentiating our regions better, right? So differentiating here means that if you're in the white region, you have sort of generally higher values versus if you're in the green regions, you have lower values. And it's not, sort of distinct enough across the board to have a cutoff, but at least there seems to be some difference in behavior when these sort of bifurcations and switches in behavior happen. So that is promising. And then the other bit, so this is a version where we did the same thing, but on the ordinal partition network. And in this case, I think we have even clearer differentiation, right? So especially in this like wider region in here, we're seeing sort of big jumps. I guess they are too, but we've also got some sort of differences in terms of our representations for the sort of the other regions where we have bifurcations.
So Liz,
yep.
Can I ask a question here? Mm-hmm. So let's go back to the picture.
Yep, trying. There we go.
The green regions are the regions that is periodic. Is that what it is?
Yeah.
And then the white region are chaotic.
Chaotic. Mm-hmm.
And then from x-axis, it's just different parameters as before. So my question
so,
is,
so this is the, yep. So this is the entropy. This was, I forgot what P was, periodicity score and M.
so in some sense that in the middle column that I'm focusing on is that you have those three measurements. One is periodic score, one is a normalized version of the persistent entropy, and MD is sort of this heuristic measurement.
Yeah.
So
the heuristic.
idea
That's a better way of saying it. Let's call it the heuristic. I like that.
Heuristic, yes. So in some sense that, what you're comparing is to say that perhaps it doesn't really matter how I'm really converting the information from the persistent diagram. It feels like so for example, in the middle, like E prime, right? This is one, I guess this is one that is really related to persistence, where the P and M, those are other heuristics, right? Yep. So, and then your argument would be that, if I look at those three plots, they all seems to be at some stage differentiate between periodic and chaotic, but your argument is a middle row, which is the normalized persistent entropy. Would you argue that that is the one that is the best?
Yeah,
I see.
Yeah, okay. And the issue that we're dealing with right now is I don't have a sort of quantifiable way of saying that, but it's, visually the differences are much clearer in terms of the entropy. And on top of that, I think the differences are clearer than when you start getting into the way that people were doing it before, which is like just with standard graph measurement techniques, right? Because we're still starting with the same input graph that they had, right? So here's a network representing my time series. Now figure out what's the difference, right? And these, so there's sort of the regions where, yeah, we're still doing a decently good job of differentiating, but like, stuff in here, there's sort of slopes that are not particularly helpful for trying to see the difference. Whereas we start seeing jumps, I guess maybe this periodic one is doing a good job of seeing that jump, et cetera. So it's not a perfect classification tool, but in terms of representing overall structure, I think we can argue that the persistence diagram itself is going to do a better job of that than just looking for like average out degree.
Yeah. Okay. So I guess in the second sort of very thick green region, it feels like everybody works pretty well because that seems to be pretty obvious, but it's really the first very thick green region where the persistence is picking up a bit more periodicity than the other measurements.
Yeah.
Yeah. Okay, cool.
Yeah, we did it on a bunch of different things. I'm not going to worry about that for right now. So here's the other place that I think we excel in terms of using persistence and TDA more than just like straight up analyzing standard network analysis techniques. So if you start doing signal to noise ratio results, so which way does this go? Higher signal to noise means less noise. So I've got less noise going in this direction. So this is noisy, more noise added to my signal that I'm inputting to this whole procedure. So if I have a signal to noise ratio of 0, then yeah, I should expect that nobody's going to do well at all in terms of trying to understand anything about differentiation. What's interesting for us though is that you can start seeing a very clear split in terms of chaotic versus periodic behavior the more noise you put in the system. So like if you look at the sort of standard graph model analyses, right, there's not really a whole lot of differentiation between the chaotic and the periodic kinds of output values that you're getting. But, for a decently large amount of signal noise ratio, I'm still seeing some differentiation between the persistence-based representations and sort of like how far apart they are and how much different information we can get. Right. So this is all sort of a product of the fact that we have, stability theorems and noise resilience promises that come with persistence that I think are very useful in cases like this. Okay, so I'm going to switch gears entirely. I forgot what the timing was, Bae.
You have roughly another 25 minutes.
Babble as long as you want.
Yeah, 25 minutes. So you're good.
Okay. I got time. Okay, cool. All right, so let me talk about some newer stuff that we've been messing around with more recently, which is how do you start sort of using, have you talked about zigzag persistence at all in class?
No, I haven't.
Okay, here
So
we
you
go.
can give a
Let's get
high
ready.
level picture of it.
Okay, right. So here's the game. So before we had filtrations on simplicial complexes where inclusions always went one way, right? So you always had a growing simplicial complex. You always were messing around with one parameter going in one direction. And so you can start, so you've got inclusions going in one direction, and that gives you persistence modules where you've got vector spaces with linear transformations going in one direction. Turns out that you can get rid of that assumption and all of the theory still works. So what I can do is I can give you a sequence of simplicial complexes where inclusions are now allowed to go either direction. So the zigzag part of this is that very often you'll draw these kinds of pictures as like K0 included into K1 and K2 is included into K1 and then K2 is included into K3, and you start doing these zigzaggy patterns of what's going on. But what I've got now is a sequence of simplicial complexes. Inclusions can go either way. So another way of thinking about this is you can have insertions or deletions in terms of your simplices, but the math all still works. And so I still get a sequence of vector spaces. It's just now my linear transformations go in the direction that followed whichever way my map was going on my simplices. Yep. And so this is what we're going to call a zigzag module. And so the theory tells me that I still get persistence diagrams the way that I want to. So there's this fundamental paper of Carlson de Silva that I think is a lovely, lovely read. But the idea is that I can still get persistence diagrams the same way I did before, but now I need to interpret them differently. Okay, so once I get to the point that I've got these zigzag persistence modules, I can go try to understand essentially where do things appear and disappear. So here's a rather simplified example. I'm hoping the green shows up. So there's supposed to be a vertex here and a vertex here. But I've got a sequence of simplicial complexes where basically stuff is included and removed at every step, right? So I sort of obviously have go back. I have a circle, a triangle here that sort of persists in here. I've got a blue triangle that shows up in here and lasts over here. I've got another connected component that's sort of hanging out over here and stays to this bit. And so what I have now is points in my persistence diagram representing this stuff. So I believe this is the one-dimensional diagram. So this is, let me make sure I've got my indices marked. So I believe my indices are currently labeled as K1, K2, K3. And so this is sort of like K a half and K 3/2. Let's find out if I'm right. And so if I look at my one-dimensional persistence diagram, let's hope that I did that right. I've got a one-dimensional class that lived from K0 right up until, but not including K1. So that's this red part. And so I get a point 0, 1 here. I also have a point that shows up at, let's see, that's 2, not 3. I can add. And so I've got another blue cycle that showed up at a half and lives until 2, not inclusive. Is that how I want this to work? Yeah. So I've got my second point of my persistence diagram here. So the main trick with these examples is that we are going to interpret them in terms of sort of where circular structures show up in this sequence, not necessarily having anything to do with expanding radii. Okay, so here's a sequence of point clouds. And so the idea was, let's try to detect the range of the point clouds that are the most circular in some sense, right? And so this is sort of like barely there circle, but it's really definitely there for those middle chunks, and then it's mostly gone in the end. The problem right now is that if I were to try to represent this in my sort of standard persistence diagram framework, I've got a sequence of point clouds. They're not really related to each other. It's really not quite clear how to deal with this. And so what we can do is we can set up this relatively gigantic structure, which is I can take my sequence of point clouds I'm interested in, and then look at unions of these point clouds. And if you switch, if you pick some sort of radius parameter, you can build the RIPS complex for these things. And then, so then you get this sequence of simplicial complexes, right? So I've got the same RIPS complex parameter chosen for everybody in this particular example. And so in this case, what I'm going to end up seeing is that I've got sort of circular structure that shows up sometime around here and lives, well, right around there and then goes away, entering this particular portion. But I can take this input computation and compute a persistence diagram. And so hopefully we see what we're kind of expecting, which is that we have a connected component that persists for basically all time. So that's fine. Again, my numbering system is integers at the interesting ones I'm working with. And then I've got my sort of prominent circular structure that's showing up because I've got a circle that shows up for most of that chunk. And then this guy down here is, I don't know who he is. Oh, he must be this guy, right? So some little circular structure that showed up and filled in right away. So what does this have to do with time series? All right, so the game with the time series is that what we were doing before was we were interested in bifurcation parameters. So change a parameter in my dynamical system, get a new time series every time, and now try to see what changes and decide when it changes. And before what we were doing was we were taking each of these time series and turning them into their own individual point clouds and then trying to see what happened. Or sorry, turning them into individual point clouds and then turning into our own persistence diagrams. So what we're going to do instead is basically build a single persistence diagram that encompasses this whole pile of information that we can then read off bifurcation parameter information. So I can still take each of my point clouds, turn them into take each of my time series, turn them into a point cloud. And then based on that, I can build this zigzag module. Now, due to space constraints, I believe you have to read from left to right. So this guy over here is included into this one, and you just keep going along, right? And so for nice choices of parameters, what we end up with is a resulting persistence diagram, which hopefully encompasses what's going on. And in particular, if I was interested in that starting input time series data, I can then go back here and read off the fact that I can see a one-dimensional class that's born at 1 and dies entering 7, which tells me something about the fact that there's circular structure in this particular picture that starts at 1 and lasts until approximately time 7. So now the interpretation here is those indices you should be thinking of as related to the bifurcation parameter. And so what's changing? So, all right, so here's an example on slightly more realistic data. So this is the Selkov model for the glycolysis. Really what you care about is the fact that we've got some parameter that I can screw around with. I think we fixed A to be something, I don't remember what right now, but B is a parameter that I can change. And so what I can do is I can run this whole system on this glycolysis setup. Oh, wait, did I not do that? There we go. I can run this system on this whole glycolysis setup and go check the fact that I have a point at 2, 8.5. Go check which bifurcation parameter values that corresponds to and conclude that I probably see some sort of bifurcation happening, entering 4 and entering 0.8. I don't think I've got this on these slides, but that is also what is well known if you actually do the theory computation to try to figure out where the bifurcations happen. So this agrees up to the choice of sort of how discretized our bifurcation parameter we were working with. So let's see. So that's pretty much the idea with this whole buzz method, was to take our time delay embedding, turn it into RIPS complexes, turn those into some giant zigzaggy module looking thing, and then come up with a persistence diagram to represent it. Okay. Yeah, and there's lots of things that we want to do because as with everything, there's always more stuff to do. So we're messing around with sort of other choices of featurizations. The thing I'm playing with the most right now is how to put back weighted and directed info based on these network guys, but then also trying to combine some of these network representations with these zigzag module representations to see if we can clean this party up, because zigzag is notoriously bad to compute. It is, yeah, you thought persistence was bad. Zigzag's a hot mess. And so we're still trying to figure out how to make this reasonable computable time-wise for somebody's definition of reasonable. yeah, there's parameters to choose. There's all sorts of stuff to do in that general direction. Okay, so from here on out, I'm just going to babble about pictures for Bay because you had specifically asked me about other stuff, which I can kind of talk about at a high level. But before I go on to other things, are there questions about the time series analysis applications I've been talking about? Zigzag does kind of blow your mind the first time you see it, so I'm sure that's not helping anything.
All right, I think we can keep moving, and then
All right, here we
and
go.
then we can come back.
Okay, so I'm just going to talk a bit about sort of other things that my group does. So, so just for context and background. So my job now is in this sort of engineering style department, which I guess you all are in CS, I assume, right? So this is probably, it was surprising to me when I got there because I went from being in a math department, which runs graduate programs and funding and things very, very differently than engineering style departments. But our whole department is very, very interdisciplinary, which is great. And so this has led to a lot of fantastic collaborations and working across spaces that I definitely wouldn't have necessarily known about. So everything that you saw now is the work of, so my collaborator Faraz Kassaone is in the mechanical engineering department here. He's also my husband, he's over there. So you say hi.
Hi, class.
There we go. He says hi. And so his graduate student, Auden Myers, and my graduate student, Sarah Tomachko, have done the lion's share of all of this work that we've been talking about. And we've got all sorts of sort of various projects we've been working on related to intersection of time series analysis and persistence and things like that. Other things that I do. So I've been working on a lot of like, how do you actually get from topological signatures into some form of representation you can use with machine learning, right? So this has involved a lot of things with like, how do you take persistence diagrams and do this? And more recently, it's been sort of how do you take graph-based topological signatures, so like Reeve graphs and mapper graphs and things like that, and find ways to turn those into some sort of machine learning statistical representation that you can play around with. And so that's been fun and interesting. A lot of this then comes down to if you're going to do actual applications with real biologists in this context, what do you do? Okay, so I've been collaborating a lot with, so this is Dan Chitwood right here. So he's his affiliation is CMSE and the Department of Horticulture. So he's a plant biologist. And so he has this beastly scanner, which is, so this picture was taken before they literally built a room around this giant box. So this giant box is a giant lead box that is very, very heavy and is in the basement of the plant biology building. And he puts various plants into this scanner and we get all sorts of lovely scans, X-ray, 3D X-ray CT scans of plants. So for instance, so one of the projects we've been doing most recently is taking, so we've got these barley panicles. So we put all these barley panicles from this long evolutionary experiment into the long in the sense of they've been running this experiment for like 50 or 60 years. And so we got access to these barley panicles. And so we can take our barley panicles, put them into the machine, and we get these scans. And so this is the, after doing a bunch of cleanup to get rid of the hairs and things, we've been mostly studying the seeds. So this particular project, we were interested in understanding the relationship between evolution and the seed shape. And so Erica Mezquita, who's right here, so he's a graduate student with Dan Chitwood and I, did a whole lot of processing to try to get to the point that we actually have individual seeds from these panicles. So he took these panicle scans, separated them out, and did a whole lot of cleanup. And so what we've been doing is trying to represent shape and structure of barley seeds in a way that we can actually start doing statistical analysis. And so what we've been doing is messing around with what's called the Euler characteristic transform, which is a way of getting a filtration on your space where, like, okay, so I've now got this embedded shape in 3D, which is my little barley seed, and I pick a direction and I can define a filter function based on that direction. And you can compute any of your favorite topological signatures on that. The simplest of these is the Euler characteristic. And so we are just computing Euler characteristic based on these directions. And so if you take your seed and you do Euler characteristic in a bunch of directions, a bunch in this picture is 3, but in actual applications is like 70. What you can do is you can take this seed representation and turn it into this very long vector having something to do with this changing Euler characteristic transform. And so we've been using a lot of that for like trying to relate what we're seeing in terms of differentiating the shape of the barley seeds with the genetic information and the evolutionary information we have from the plant biologists. And so, yeah, so these are other people in our group. So Sarab is Bay's former student who is now a postdoc working with Dan and I. So he's been doing a bunch of things related to this and mapographs and some other stuff. Michelle actually runs the scanner. So this is her job is like really trying to figure out how to do all these scans. There's a lot of magic in terms of getting from an input scan to actually an output, or so an input plant to an output scan that's actually nice and usable, and it's an art form. And Tim Ofelders is my former postdoc who's been working on a lot of these projects. And Kayla is currently doing things, not necessarily with this, but they've been doing things with tree rings and forestry colleagues. So we've been doing a lot of fun stuff with that. So let's see. The other fun things that I do relate to like graphical signatures and the very, very theory side of things of how do you represent, so you can construct Reeb graphs, which you may or may not have talked about in your class. In any case, you get some sort of graphical representation of your data. And then what do you do to try to get from I have a Reeb graph and now what do I do for some sort of statistical analysis? And so things related to like drawing Reeb graphs, simplifying Reeb graphs, coming up with metrics for Reeb graphs, proving things about convergence, right? Our very own Bei Wang is, I think I stole this picture off your website, probably should warn you about that in advance. But yeah, so lots of interesting things in that direction. And then I go off the theory deep end and have all sorts of fun with like hypergraphs and categories and theoretical, very, very theoretical stuff. So Shelley Candela is an expert in finite topology and sort of how do you do things like topological complexity. So she's been a postdoc in my group for a little while, and Christopher Potvin is a new graduate student working with me who's doing persistence and hypergraphs and how you actually do things with like slightly less nice representations. So let's see, I think that's it. So yeah, that's a few of the papers related to what I was talking about. I should also mention, I forgot to put it on the slide again. Everything that I've got in terms of code and representations here. So we have a Python package called Teaspoon. So you can find this on my website or on GitHub. Basically, we've taken all of this time series analysis work and put it into an open source Python package, which is becoming more and more usable, largely because Auden and Sarah have been a fabulous job of helping clean up our code and make it nicely pip installable and all sorts of beautiful things. So everything I just showed you is available for computation. Other than that, I don't know where we were with timing, babe, but that's most of what I've got. I'm happy to answer questions or babble about whatever other specific things you wanted to hear about too. So.
Yeah, so great. Let's first give a round of applause for amazing talk. And any questions about what we discussed here?
So when you say Reeb graph drawing, do you mean visualizing the Reeb graph or turning it into something like a persistent diagram that can be fed into machine learning?
So this particular grant is related to, so where do I want to start with this? Okay, so Reeb graphs, so the whole idea with Reeb graphs is Reeb graphs are, they come with a space and a function, right? So you've inherited some sort of function from the topological space that you got it from. Does that sentence make sense?
No.
No, okay. So so Reeb graphs, hang on, I need better pictures. Give me a second, let me get slides from another talk. There we go. I gave a talk about this recently. I can't find anything. Where am I? This one. Well, this is old slides. So the idea with a Reeb graph is basically you take an input topological space with a function and collapse connected components, right? So all of the points that are at the same function value, this will be easier to see, all the points that are at the same function value get collapsed into a single point. And so what ends up happening is you have these graphs that inherit this, this function value from the original input space. So what we've been interested in terms of trying to draw Reeb graphs is, when can you draw a Reeb graph, in particular in the plane, right? So basically now I have my y-axis drawing part of it given to me. What can I do in terms of x-axis coordinates, and when can I promise you that this thing is actually a planar representation? So so like this guy, no. So like this guy right here, right? So this is a particular drawing of a Reeb graph where there's no way to actually draw it in a way that's planar, in the sense that I can't respect the y coordinate locations. I can't respect the y coordinate locations without having some sort of crossing in my drawing. And so in this case, we were interested in this smoothing operation where you can sort of apply, you can change your Reeb graph slightly in this sort of like slowly modifiable way, in a way that you can sort of see if you can eventually get to a planar representation, or what happens. Yeah, so this is, so we didn't quite get to doing this, but this is what the partial work and the results of this sort of idea are what turned into our sausage paper that we're going to present in, when is sausage? June?
Yep, June.
Sometime June.
Sorry, sausage is a conference.
Anyway.
It's a
sorry, sausage is a conference. Yes, I forget that. Yes,
Symposium of computational geometry.
Sausage is a conference. Yes.
Okay, that's not exactly what I mean, but that's what I mean. Okay, any questions?
And I guess the one on the bottom where you say mapper convergence. So from the diagram, it looks like you're saying that as you reduce the intervals, it's going to converge to a Reeb graph.
Yes.
And so what are you trying to do with that work? That are you trying to get from mapper to a actual Reeb graph? And
yeah. Yeah, so the idea here is, okay, so based on some of these things, we've got ways of coming up with metrics on Reeb graphs, which turns into ways of coming up with metrics on mapper graphs and things like that. And so whenever you're talking about these metrics, they're supposed to basically keep track of both the space and the function value. So this is sort of like the pair of that data is what I start with, right? And so Bay in my paper, what year was that? 2016? 2016, yeah. Because I was giving birth. You had to give the talk because I was giving birth. Yeah, that was a good day. So the idea is that essentially we've got these metrics that you can use to compare Reeb graphs. And so what we can do is exactly what you said, right? So prove that for finer and finer interval covers, that you can get closer and closer to the sort of correct ground truth, the Reeb graph, the underlying Reeb graph in the middle. And so, yeah, so the sort of long-term goal then would be to mess around with things like, can you say things about mapper graphs directly in terms of coming up with metrics? Can you do like Cauchy sequences and all sorts of other fun things? The stuff that you can do once you have a metric. And the sort of the place that you get this metric from is from essentially defining these things as categorical objects. You get these category theory frameworks. And so, it's not on this page, but so Anastasia Stefani was my PhD student from when I was at Albany. He's got this lovely thesis where he basically goes to like the massive generalizations of how you come up with these metrics. So just for context, this thing right here is his proof of the triangle inequality. I don't know. I still love that thing. It's a beast. It's the biggest diagram I've ever put in a paper. But you can use this sort of categorical framework to come up with this like way of coming up with these metrics, which you can then use on all sorts of different things.
I see. Cool.
I have a more generous question, I guess. General question. So if I want to get more into doing more theoretical research, I guess like stuff that you do, I think is really cool. What are some background that you think that is like really important to start like learning and get really good at? Because I know like category theory is like really hard.
Yeah, and I can justify that too, because man, like if you had asked me 10 years ago if there was any chance I would ever do any research in category theory, I would have laughed in your face. And yeah, so I promise it is possible to learn this stuff. It does not come easy to me by any standards. So I think That's a good question. And I've been struggling with this with my graduate students too recently, of like, how do you figure out exactly what background you need for a lot of this stuff? And I think what's cool about TDA is it's got it draws from a lot of different background directions and sort of background topics, and different people's expertises are useful in different ways. So I think having a decent working knowledge of the algebraic structures is useful for the persistence diagram stuff, right? So if you're going to understand how persistence modules work, so like I'm not going to touch ephemeral modules with a 10-foot pole, but I sort of understand that they exist because you can do sort of weird algebraic things that get you sort of nasty, basically where the line goes from being like computable to nasty is sort of a good thing to have a working knowledge of. I've found that the graph theory background has probably served me the best, because I tend to do a lot of like combinatorial topology kinds of things. And so graph theory and simplicial complexes are sort of my default. And so having a strong working knowledge of that has been very useful. The category theory, I sort of, I use it as a means to an end. So it's more of like a structure I can use to come up with these frameworks and then try to like ground it back in whatever field I'm trying to work in. So I think the solid algebraic topology background is probably also what's going to be the most useful, right? So a lot of the category theory ideas come from, well, in my opinion, come from a lot of the ideas you're going to learn in an algebraic topology class, right? So for instance, functoriality is sort of a generalization of like the fact that I can take a map on two topological spaces and turn it into a map on homology, right? And it behaves and does all these nice properties. Category theory, right? Functors are really just that, but I've replaced, spaces with some other category I don't know, and homology with some other category I don't know, and I happen to have all this other structure I can use. So I guess that's kind of a non-answer to your question. There's lots of different ways that you can get at it, and I think the trick is taking your expertise in whatever field you're working in and finding a way to sort of fit it in. Learn the other pieces that you need, but how can you sort of take that expertise and bring it into the rest of the field? One other thought before I stop babbling about this is that I think this is why the sort of TDA community and applied topology community is very, very collaborative, which I love, right? And so we end up working with other people who have sort of different expertise in sort of different places, because I would love to think that I could learn everything, and I don't think that's possible. But so for instance, like if I'm going to do a biology project, there better be a biologist around, because I can't do biology at all, right? And so I'm not going to make any valid conclusions based on my topological methods if I don't have a biologist around to tell me when I'm being silly, right? So that's sort of, I function very, very collaboratively, and I think that's why.
So Liz, I think as a conclusion remark, I would like to ask, because one of this topic to conclude the semester is talking about what is the future of TDA, right? Like, I was wondering, we have been discussing about it on and off whenever we touch a topic, but I was wondering, what is your opinion about sort of what do you think are the exciting directions from your perspective over TDA research?
Do you want this theory-based or applications-based?
Either or both.
Yeah. Theory-based is harder for me to answer just because I tend to follow the theory based on what I'm interested in with applications. Application-wise, the places I'm seeing the most exciting results coming out. So I guess, let me back up. So when I was getting my PhD, everybody was still trying to figure out the theory and how to actually compute anything and how to like make anything feasible at all. And then generally run around convincing everybody that we were useful. And what I think is really cool now is that there's applications that are popping up where it's becoming very clear that these sorts of additional structure that you can find in topological methods does actually help in the application. And the places that I can see that happening, especially, I don't do any of this, but like the neuroscience community is doing all sorts of really cool things in terms of trying to understand sort of underlying structure in the brain and neurons and all sorts of other things, where again, the sort of additional work that you're willing to do to compute persistence representations or topological representations is then worth it because it actually finds structure that the other stuff couldn't. I think a lot of the biology, so biology in the more broad sense, right? How do you do things related to like genetic activation networks and all sorts of other sort of representations of things that you can use where you can where you can analyze data using a different viewpoint where the structure is useful. Those are kind of the two big ones I've seen most recently. Yeah, so I think maybe that's where the field is going, right? Is, you know, I love the theory part of it, but I think the super exciting directions I've seen recently are how do we take the sort of powerful theory that we've built and actually find ways to interact with domain science in a way that does something useful.
Yeah. Okay, so so I think we're a bit over time, but I think let's thank our guest lecturer one more time. And also I'm going to stop